What time is it? Oh, by the way, Michelle, is it is it uh okay just say Michelle, or is it better to have your name
Just Misha is
pronounced?
fine. Yeah, yeah.
Yeah, because I it's so yeah. Okay, yeah, I will. Yeah. So hello everyone. So welcome to AsiaGraphics webinar session 38. So my name is Yichao. I'm a session chair today, and I'm from the University of Tokyo. So today we will have two very good, very wonderful talk and speakers today, and Michelle and Min. So the first talk is about processing of weird geometry, and the second talk is about visual design abstraction with generative models. So let me first introduce the first speaker. So sorry. Michel currently is an associate professor in the Department of Computer Science and Operational Research at the University of Montreal, where he leads a geometry processing group. He's currently visiting the University of Tokyo in Garage Lab, basically. So we are working together right now, and his group is aimed for creating new tools for artists and designers and professionals and hobbyists. So to improve the modern geometry and processing and animation. So yeah, let's welcome Michelle. Oh, sorry. And I have to stop sharing.
Great. Let's share the screen. So there. Okay, should be able to see the screen.
Yes, yes, yes.
Great.
Yeah.
Thanks to Chao for the introduction. So hi, thanks for this opportunity. Um, so I'm going to be talking about weird geometry. And before discussing what is weird geometry anyway, I would like to say what's proper geometry or decent geometry. So mostly geometry processing has focused on decent geometry, like point clouds, or maybe implicit functions that encode geometry, or maybe meshes or stuff like that. And for the most part, our algorithms in the current toolkit that we have work pretty well on them, right? Like if we have point clouds, we can do surface reconstruction. If we can do normal estimation, for example, from a point cloud, right? Or maybe we can even measure insidedness, right? Like, or insideness. We can tell even from some weird open meshes or open point clouds, doesn't matter. We can tell that you're roughly inside this object or roughly outside, right? So this is called the winding nugget. And uh, the thing is, not all objects, not all geometry that we get in real life is as nice as perfectly sampled point cloud or meshes, stuff like that. There are some domains, for example, in 3D sketching, when people would create those kind of 3D curves, right? Bunch of 3D curves. And those are not exactly point clouds. Those are not exactly meshes. They're a little weird. And turns out they break a lot of assumptions that all the previous work has focused on, right? So this is not the only example. So in 3D sketching, you can create those curves or maybe sometimes ribbons. So they have normals and some width. But also for point clouds, sometimes the point clouds are bad. So for example, they come from misaligned scans and they have weird, you see the kind of duplicated geometry that doesn't work well. Maybe some details are inside and so forth. It's a bit of a mess. And even, instead of perfect manifold meshes, sometimes you get those kind of polygon soups. You see that those triangles are kind of disconnected here, right? This is common in lots of shape repositories. If you just download something from some standard shape repository, you'll get all those kind of crappy triangles. Right. So my question in general is how to make geometry processing, all sorts of reconstruction or normal estimation or measuring whether you're inside a curve sketch or outside directly, right? Like, can you still work on this weird geometry despite the fact that it doesn't work with all the standard methods? And kind of the so this geometry is super common, and the overall question is, how can we do anything useful with it? And one kind of naive approach is to say, wait, sketch, not sketch, you can just like sample points from these curves and plug it in your favorite point cloud surfacing network, and it will produce something. And turns out it doesn't work well, right? So like if you try doing that using all the standard methods, they most probably will fail. Yeah. And the reason for that for this particular input is because curves are very sparse, right? So if you think of like actual sampled point cloud would sample the whole surface. Here you sample just a tiny bit of the surface. We as humans might understand what the surface is, but like standard reconstruction method will fail, right? Um, and the same for normal estimation or weird kind of reconstruction. So if you have a misaligned scan, I don't know if you can see, but like here points are sampled all over the place, like little jittered. So all the standard methods will produce some weird artifacts. So that means that some assumptions are broken, right? So one of the problems, one of the kind of the fundamental reasons why some of the standard methods fail because they assume they have some discrete decisions, right? So discrete decisions, there are some binary or maybe integer variables that decide whether, for example, 2 points are connected, right? So you look at 2 points and somewhere along the algorithm you say, okay, well, maybe they're connected, so I can combine them into a single triangle, right? Or maybe for ribbon input, if you want to surface this thing, you probably want to be able to tell whether the ribbon is pointing, the normal is pointing towards you or away from you. And this is also a binary decision that you have to make at some point in your algorithm. And sometimes it's just a wrong decision to make, right? Like if you're thinking of some stuff inside the surface, like here, it's hard to tell which way the ribbon should be oriented because it's not the part of a surface that you want to reconstruct, right? And so forth. And for maybe for these kind of polygon soups, you want to be able to tell whether triangles are connected actually, or they form a true boundary of the surface. And all these discrete decisions, if you do them wrong, you're in trouble, right? So that's going to propagate throughout your algorithm, and you're going to die trying to fix them. So my kind of approach in general, what we do in our group is to essentially formulate some continuous theory, discretize it, and delay or avoid these discrete decisions altogether. So I'm going to illustrate this approach on a few examples. And the idea is that if you have something continuous, and I'm going to be talking about like actual math, well, mentioning some math behind it, if you have something continuous, some energy functional that is variational, and you just minimize it and discretize it, turns out there's some robustness kind of that is baked into this process that doesn't care about your noise in the input or maybe sparsity. It somehow is more robust to this. So a few examples. So let's start with surfacing these 3D sketches, right? So you have this is as your input, and your goal is to find a surface that should surface this 3D sketch. And the first thing, if we try to think about it, the first thing that we have to notice is that actually this is ambiguous, right? Like all these surfaces satisfy all the standard requirements, right? They pass through the curves, they're smooth, whatever, right? They're all good. And for this kind of torus shape or something of that sort, all these surfaces are good, right? But as humans, we only like one of them, probably, right? So for this input, you probably would pick cylinder. For this, you would probably pick a torus, right? There's something about this that makes sense to us. And to cut the story short, so maybe in this example as well, see the curves. There's no surface, but you can imagine it pretty well, right? So um, there is a kind of a working theory currently that is used in this literature that the surfaces we want, the surfaces humans tend to envision, have something to do with principal curvatures. So essentially, the idea is that these curves that the people draw in 3D or 2D, those are not any curves on the surface. This is not just random, we're imagining a surface and just randomly drawing curves there. Those are lines of principal curvature, essentially, up to small details, right? So essentially, one of the curves will always show you where the surface bends less, right, or least, right? Like here, for example, the surface is in this direction is straight, and the other curve will be showing the kind of the maximal curvature where the surface bends the most. Yeah? So this is the idea, and this should give us some instruction on how to create those surfaces. So in this project, what we did is essentially we encoded the function we're optimizing. We represented it as neural implicit. So for every point, there's a gigantic network that for every point tells you whether you're how far you are from the surface, either from inside or from the outside. And we optimized the parameter of this network, so trained, such that, first of all, the principal curvatures of the surface are parallel to the drawn curves, right? So you can see here, you can see that those are directions of principal curvatures. Here, for example, they show this is the direction where the surface bends, I guess, more, and the perpendicular direction is where it bends less, where it's straight, for example, here on the ear. And you can see that one of those directions is always parallel to the curves. This is what we want. So here, for example, this direction is parallel to the curves, right? So that's one kind of line on the wish list, what we want. This controls the shape of the surface given the curves. Then we would like these principal curvatures to change smoothly as we walk along the surface. So this you see that here they're a little wobbly, here they're a little more smooth. So this is the correct smoothing requirement. And we of course would like our implicit function, which to be zero on the curves, to make sure that once we extract the zero iso level from this implicit, we get exactly the right surface. Right? So this is like an arbitrary example of a applied problem. But what I would like to underline here is that all these kind of points on the wish list, all these bullet points, like this one, for example, we would like to minimize the value of our implicit on the curves, right? And it's some kind of integral, right? So in this case, it's integral of just absolute value of the function. And we formulate all the other terms in terms of these integrals as well, right? So in the end, what you're minimizing for your variable is the function f, right? And you're doing this variational optimization, and because of that, because all your energies are just functionals, right? So some energies of your function, the optimization becomes robust to noise, right? So there's some discussion of why this is the case, why it works well, but this is the idea. This is a continuous optimization that you discretize at the very end. You don't make any discrete decisions, and this turns out to be working well. So if you look at a few examples, our result is somewhere here. It tends to work better than all the previous approaches. And also, as a side product of variational optimization, you get smoother solutions that you would want to get sometimes, right? So this is kind of the caveat. All right, so the second project where I would like to demonstrate what we do is about winding numbers. So imagine yourself, you have this curve on 2D on the plane, and you would like, as you're programming a game or something, coding up some engine, and you'd like to be able to tell whether you're inside or outside, right? So for this point, you would like to return inside. For this point, you would like to return outside. Okay? So if you did any sort of coding of that sort, maybe you know that the standard way to do this is, well, one of the standard ways is just given the point, shoot a random ray and count the intersections, right? So if you shoot a ray and, for example, doesn't matter where. So for example, for this ray here, you would get one intersection. So it's an odd number. That means you're inside. Yeah. If you shoot a random ray here from the outside, you'll intersect the curve even number of times, right? So you measure whether it's odd or even, and you're done, right? So more precisely, and this is used all over the place, right? So this kind of inside-outside tests are used to voxelize shapes, to produce sign distance fields, to tetrahedralize things, and so forth. It's a very basic and important test in geometry processing, right? So this is all good if your curve is closed, but if your curve has a gap, curve has a boundary to be exact, right? So here, 2 points are the boundary of the curve. How would you do that? So the kind of the very standard way of doing this, of generalizing this test, is now saying, okay, well, now instead of shooting just one ray, I'll shoot a ton of rays around the point. So here, for example, I'll shoot all the possible rays around the point, and I count the number of intersections for each, and then I average. So to be exact, instead of measuring whether the number of intersections is odd or even, I'm going to do slightly trickier version when I'm going to shoot a ray, any ray, and count the sign of the intersection. So if I'm intersecting the curve, you see that it's oriented. If I'm intersecting it from the left, like here, I counted, for example, as +1, right? If I intersected from here, for example, from the right, that would be -1. Yeah. So now I have a signed number of intersections for each ray, and I average that. And that gives you this nice function. You see that when you're inside, most of your rays will return +1. Some rays will escape through the hole, but that's going to be a minority. Once you average out, it's going to be fine, right? Once you're outside, most of your rays are going to have some kind of, you'll have a nice kind of outside result. And if you're here in the hole, half of your rays are going to be maybe intersecting from the inside. So they're going to get +1s. Some of them will return 0, right? So once you average that out, you'll get some sort of 0.5. So it's a nice field, and this function is called a generalized winding number, right? So this is what we study, and this is kind of very natural notion of whether you're inside or outside, right? It works in 3D. Like here, for example, you see a kind of a head with a camel head chopped off, so it has a boundary here. There's a boundary curve, and you can see that when you're inside, it returns you 1, and when you're outside, it returns something, close to 0, right? So this is kind of a nice object in general, and you can see that because we're now counting intersections with this sign. So from here, for example, we're intersecting the curve with any ray would intersect twice from the right, so we counted as -2. From here, for example, if you shoot this ray, it's going to intersect the curve on once with a plus, once with a minus. It's going to cancel out, so you're going to get 0. Right? So winding number naturally captures those how many times the curve or the surface spins around your point, right? So it's kind of an interesting object in general. So now let's kind of think how to compute this well. So if we kind of write down this definition of averaging all the numbers of signed intersections, you'll get some kind of integral like this. So this is the signed intersection number for a ray, right? And then you average over a little circle that just tells you where the ray is pointing, right? And this is just some scaling factor, right? So to compute a pure average, right? So for example, for this ray, you get 1 intersection. For this ray, you get -1, then +1, right? Because you're intersecting the curve on from one side, then from another side. So in total, 0. So if you were to implement this algorithm, probably you could write just this integral, discretize it somehow, like shoot 100 rays, average them, right? For each ray, compute the sign intersection. Right? And we know how to intersect rays with geometry, so no big deal, right? So you could do that, but it's slow, right? So what we looked at is that, look, if you shoot the let's say this is the endpoints, right, of the curve. So if you shoot the ray anywhere here, you'll get 0 intersections, right? Moreover, as you're crossing this point, you do start, so your ray is now intersecting here. You start intersecting the geometry, but the two intersections, you always get two intersections and they're going to cancel, right? So up until this moment, when you hit the endpoint, you're always going to get 0, right? So this is the first. So you can imagine, like, as you're scanning this ray from here to here, you're getting 0 intersections, 0 intersections, 0 intersections, and then you get hitting an endpoint, right? And once you hit an endpoint with this ray, now you'll get +1, right? So every time you'll hit exactly one your curve once, right? Until you hit another endpoint, and then you get 0 again. So essentially, you can think of that the only thing that matters is this part. Like if you think of the little circle around your point where you can, that just shows you where to shoot the rays. The only thing that matters is where your endpoints project, right? So in this little arc, the number of signed intersections is constant. So instead of like shooting 10,000 rays and averaging them, I can just shoot one ray in this region, compute the number of intersections there, and one ray in this region, right? Because we know that the number of intersections for any ray in this region is constant. So I shoot one ray here, one ray there, and I multiply by the length of these arcs. That's the total integral, right? So that's it. That's the whole algorithm for 2D, almost. Yeah, so the whole idea is that this angle that just comes from the projection of the endpoints on the little circle around your query point, this is your winding number. That's all it is. There's a bit of a caveat, right? So if you, from one hand, on the one hand, then, if you change your curve but do not change your endpoints, your winding number mostly doesn't change, right? Sure, the curve loops or does whatever else, self-intersects, it doesn't matter, but it's all going to cancel out, right? So here, for example, you can imagine shooting a ray through this mess. It's going to be still +1, right? Like 1, -1, +1. Yeah, so it's going to sum up to +1, right? So this all works well until the curve goes the other way, right? Then suddenly you need to the structure, the fact that like here the number of signed intersections doesn't change and here it doesn't change is still correct, but you just need to take into account the new values, right? So for this region, the number of signed intersections is always -1. So you need to shoot one ray through each region. And it works for any curves essentially, right? So here, for example, it loops many times. You shoot like through this region, you'll get 3 intersections through this 2, right? So the winding number average was going to be like 2.4-ish, right? So this is the whole algorithm, right? So essentially, you just project the endpoints of the curve onto a little circle around your query, and in each little kind of arc segment or arc, you just shoot a ray once. You count the number of intersections multiplied by the length. And turns out that this works in 3D as well. So in 3D, it's going to be, it's kind of interesting what happens. So here's, for example, a weird object, a box. This is the boundary, as you can see, right? So here's a query point, and you want to be able to tell whether you're inside the box or outside the box. So here, what you do is that you draw a little sphere, and you project the boundary, which is now not 2 endpoints, but the whole curve, onto the sphere. You get a weird curve like this, right? So the whole idea stands from before. Now, if you look at this weird curve and these regions on the sphere, the number of signed intersections of any ray with a surface through in the region stays constant, right? So no matter which ray you shoot through this region, you're going to intersect it the same number of times. No? So this is kind of the trick. So you can compute the same winding numbers in 3D as well by essentially taking the boundary of your surface, which in this case, for example, is the whole curve, projecting it onto the sphere around your Curie point and just shooting one ray through every spherical region and then multiplying by the area of this region. That's all. Yeah. So it turns out that's the whole algorithm. You project the boundary onto a sphere, create those regions, shoot a ray per region, computing the signed intersection number, and multiply by the area. That's all. Sum up. So it turns out this works for any geometry, triangle meshes, parametric surfaces, whatever you want, right? And this year what we showed is that essentially this sum, you don't need to actually project those boundaries onto this sphere and like do weird decomposition of the sphere and compute those region areas. Actually, this whole thing can be computed as a single integral, right? So using something called shoelace formula, if you're familiar, it's some trick from high school geometry to compute areas of polygons. So I'm going to skip the math here, but essentially, once you do that, it's a very fast way of computing Winy numbers, faster than everything before, and still exact, right? So this is kind of a nice trick that works on, any geometry you can think of, wherever you can intersect rays with surfaces, right? So this is, again, another example where you don't, this is a truly continuous theory, right? There's no discretization until the very end. At the very end, you have to discretize, but that's very much delayed. And that gives you some method that is very robust and actually mathematically interesting. And the final kind of example that I'm going to mention is for oriented point clouds. And the idea comes from this thing that you might have seen on your microwave. There's the little kind of screen with holes. So it turns out it's not there for decoration. It's actually blocking the electromagnetic field. So the idea is that here, for example, you see like this is something called Faraday cage, right? So you see also these holes just like on the microwave. So turns out this kind of structures, how they work is that if you have any electrical potential outside, this cage guarantees that potential is constant in this cage. In other words, that means that the field inside the cage is zero, right? So for the case of microwave, the potential, electric potential on the screen is constant. That means that outside the screen, the electric field will be zero, right? So this is kind of it's a blocker, right? And just to remind you guys, if you forgot the physics here, the potential is just a scalar function, and electric field is its gradient. It's a vector in the space. So this is the trick, right? Like the Faraday cage makes sure that the U is constant everywhere on the cage. So all we did is we used that trick to orient point clouds, to find normal zone point clouds. So what we did is we took some, let's say, electric field, some function like this, linear in the space, and we place a point cloud there, right? So a bunch of points. And now we say, okay, find me an electric potential which satisfies Laplace equation, right? Find me an electric potential such that this potential has the same value on all the points. We don't know this value, but just make sure it's the same value. Yeah. So for those who are more familiar with math, essentially you minimize Dirichlet energy with this weird constraint, right? You're saying, okay, find me U such that U is the same on all the points and it minimizes this Dirichlet energy. So what it does is that you see how this field works right now. So if you enforce this constraint, it deforms like this, right? So something that was linear before, it's gonna work. Yeah, something that was linear before is now deformed. And you see that there's an isoline passing through all the points. Points are somehow gone, thanks PowerPoint, but that's how it works. right? So you see that the gradient of this field inside the object is now zero, right? So there's nothing happening inside. So that means that once you do this, you can say, oh, well, if you have some garbage, some extra points inside the point cloud, doesn't matter. It's going to get blocked, right? So you will get no normals inside. And on the actual points, you can just take gradient of this field and it's going to point sort of along the normal. We'll do something slightly more complicated in the paper, but it doesn't matter, right? So this is the whole trick. So in order to orient a point cloud, all you do is you compute this one Poisson solve, one yeah, in this case it's Poisson, not Laplace, doesn't matter. And you enforce this weird boundary condition that says that on all the points, the values are all the same. And this gives you, once you take the gradient, it will point exactly towards normals. So, and once you have those normals, you can do standard reconstruction. And this thing tends to not care about the messy geometry. So here, for example, you see in the input, there's a bunch of stuff like ribbons inside the object. It's messy, right? And lots of standard reconstruction methods just fail or produce some weird artifacts. This thing, because it just essentially computes the outside of the surface, right? Inside, it blocks everything, just like the microwave screen. It computes something that is kind of nice, and it doesn't care about convexity. It's fine with non-convex shapes. It reconstructs surfaces pretty well. So my kind of take home message essentially the way we suggest doing processing weird geometry whenever you have a bunch of noise, weird things, non-manifoldness, whatever else, is to take a continuous thing from geometry physics, minimize that, discretize, right? So, and the kind of the underlying reason for why it tends to work well is because usually the minimizers of variational optimizations are related to elliptic PDEs, and elliptic PDEs tend to be very stable and tend to produce kind of smoother solutions. So and then that transfers into discretizations. I skipped all the part about actual discretization. It's a little tricky on the weird geometry, but so for that, I have to look at the actual papers. And upon that, I would just want to mention that this is a team effort. There's a bunch of people working on that. Some of them are my students, some of them are some other universities, or some others are profs and postdocs. And upon that, this is it. Thank you for your attention.
Yeah, thank you, Misha. Yeah, so I think there is a question on the live stream, but I want to personally ask a question first. So I think in your first in the end in your last slide, so you were mentioning this continuous like optimizing this continuous function will inherently will become like a smoother, right? So you got a smooth result, and then also in the first work when you're talking about this surface reconstruction, I think that you also mentioned that most of the time the result are smooth. So I'm wondering in this kind of case, for example, if we want to, let's say we want to get a sharp corner or this kind of boundary with a very sharp transition, how is there any ways to kind of have a way to plug in, or is there any other approach to do this?
Yeah. No, you can totally do that. That's what we and a bunch of other groups are working on right now.
I see.
The trick is that you have to introduce those discontinuities somehow and control where they appear. So the standard approaches to discontinuities are something like L0, L1 norm minimization,
I
but
see. I see.
they tend to be uncontrollable. You don't know where they appear. So you need to kind of make sure, for example, they only appear on the curves. That's a little
Interesting.
difficult.
I see. I see. Yeah, I'm very interested in this because in one of the previous work I did before when trying to do this vectorization,
Mm.
and I think what we back then what we try is that we try to recognize in 2D, try to recognize where the corner first
Yeah,
is like is trying to maybe try to divide the entire problem into a lot of sub
yeah,
region or sub problem.
yeah. Yeah, you can do that. So we did that as well for vectorization. You can have a gigantic neural network that predicts where the key points are, and then you just connect them
Yeah,
smoothly. It
I
tends
see.
to work fine, but again, whenever your network is wrong and predicts a wrong key point, then you're doomed, right? So
Yeah,
it's
I see.
somehow
I see.
unsatisfying for me, but
I
it
see.
kind of works.
I see. Yeah, so I think there's a question about, I assume it's about the winding number project. So the question is, does the method break down when boundaries are noisy or fragmented?
Yeah, that's a great question.
Oh,
So
yeah.
um, I would say that it fails gracefully in the sense that, like, if you take a continuous boundary and start breaking it down, um, then your winding number is behaves exactly the same way as it would for the standard methods, right? Like it's exactly the same value, right? So
Interesting.
it's like theoretically it computes just the same thing as you would with like projecting triangles or whatever people do for winding numbers. So in that sense, it's correct. But for uh, yeah, so I think this is more in the context of meshes and parametric geometry. I don't know how you would kind of break the boundary. It becomes a little weird. Um, but yeah, an interesting question would be if you have a point cloud, can you do some kind of weird
Mm,
estimation of boundary and then compute that there? And then if your boundary is bad, how it's going to behave. So that's a question to think about.
I see. I see. Yeah, another question from me is that, so for example, that as you said, there are a lot of weird geometry or maybe imperfect geometry, right? And I think one recent thing that I learned, or at least for that last couple of years, is that I think there are a lot of this kind of generative model that probably they will also generating a lot of weird geometry or have this weird topology.
Mhm.
And do you think this kind of like the method you and your group are working on, is it also is there any new new problem or new problem to solve given this situation, given this like trend?
Right. And when you say like what kind of geometry you're thinking of generating, like is DFs kind of UDFs or
Yeah, like I think my understanding is that usually the like a UDF or SDF thing that I saw is usually more not that weird because it looks over usually quite
yeah,
smooth.
yeah,
But like I guess maybe it's getting better and better, but I still have the intuition that maybe like Mesh or point cloud, they are still very unorganized. I think it's getting better, but just like it's still a lot
right,
of
right.
unorganized or weird geometry, I think.
Yeah, yeah, yeah. No, definitely. And like there's there's all those kind of nasty problems with these this kind of generated meshes, like how to make them manifold if you want them manifold, how to repair them and so forth, because most of the time the topology is just broken. Another bunch of questions is, a bunch of papers produce splats. Can you do something useful with splats? And I think there's so many research groups right
Mm,
now
mm,
focusing
mm.
on just that. Can you like
Yeah,
deform them?
yeah,
Can you match them? Can you mesh them well? And so,
mm, mm.
yeah,
Yeah. I
lots
see.
of questions.
Yeah. Okay. Yeah, I think that's let me check again. Yeah, I think that's mostly about it. And then yeah, thank you, Misha.
Great. Thanks.
Yeah,
Thanks a lot.
thank you.
Mhm.
And then I will let me pull out my slide. Okay, my second. So yeah, and okay. Next, we will have our second talk, visual design and abstraction with generative models, and Ming will present this talk. And then Ming is currently an associate professor at Shenzhen University, and she leads special creative intelligence and interaction research group. So I think Ming's work spans from visualization and graphics and HCIs, and also she published papers at top tier conference including SIGGRAPH and CVPR, IEEE BIS and CHI. And yeah, that's welcome, Min. Give me a second. I need to stop sharing.
Yes. Okay, thank Aichao for the introduction. So let me share my screen. Wait. Okay. Um, yes. Wait.
Yes, I think. Oh,
Oh,
you need to
wait.
swap again.
Yes, yes,
Yeah,
sorry. I make a mistake. Yes,
yeah.
like
It's
this one.
no.
Yes, now it's good.
Yes, yes, yes. Yeah,
Okay, great.
yes,
Okay,
yeah.
thanks for the introduction. I'm Mingru from Shenzhen University, and I'm really happy to give a talk here. So today I'm going to talk about our recent work on visual design. Actually, visual design is kind of my research topic that I'm particularly interested in the design of infographics and data charts, which are my roots. Where I used to do research in visualization field. But recently I developed some more and more interest in computer graphics. So I work on vector graphics and also very interested in this kind of illustrative designs. So today in my talk, I will introduce our two recent projects in this direction. Okay. So let's start with the first project. This is a project about collage and packing, and it was presented at SIGGRAPH last year. So when we talk about collage or packing, I show here like two examples. Both of them share the similar layout, which is like to pack elements in a container. And specifically on the left, we called it a word cloud. So when we see this kind of visual design, actually packing things together is very challenging. Say for this design, that designers need to pack very dedicated elements in this boundary of United States. And we see here the boundary is very intricate and with very detailed contours. Okay. And if we look into the elements, there are some elements with this kind of concave forms, like the bridge. I think this is the Golden Bridge in San Francisco. And also like the bear here, which has very intricate boundaries, like the little ears and the tail of this bear. So when designers to design this collage. Actually, it takes a lot of effort to lay out all the elements nicely in this container. But like packing actually is a very long studied problem in computer graphics. So a basic packing problem goes like this. We have a set of elements, like here is a set of little monsters. And on the other hand, we have a container. And we want those monsters to fill up this container like without exceeding the container, without overlapping among each other. So it's an optimization problem. And then conventionally, people approach this packing problem in object space. Like, say we have two objects, A and B here, and researchers try to describe their boundaries very carefully with dedicated descriptors so that they can propose like geometry predicates to judge when the two objects are overlapped with each other. Um, but but like how to come up with the very dedicated geometry descriptors actually is very challenging, and it's also very hard to generalize one descriptor to another. So this make us think, what if we shift this problem from the object space into image space? Say, when we render these two objects into image space, and they become pixels. So in pixel space, when we judge the overlapping or like empty space, we just need to count the number of pixels in their joint regions or in empty space. So, but a general rendering won't work for an optimization problem. So the key power that we have here is that we use differentiable rendering so that the whole process can be the laws that we defined, image space can be like back propagate into the object space. And there are many benefits that we work in image space. Say, because of that, we render everything into pixel, so it's object independent. We don't care what the objects are, and it's relatively with limited complexity because we deal with the grids of the pixels. Okay, so let's preview some results. This is like we have two different containers, S and I, so we see how these little monsters, they gradually fit up the container. And here we zoom into a local part here. We see that actually they are packed very nicely. And this method is very robust to the way how we initialize those monsters. Here we initialize them along the skeleton, and we see they can nicely packed. And because the container is just the area of black pixels, so it's very flexible to define where to be the where the containers are. Here I draw some white stripe to block the monsters to get across, and play with different image space loss functions. We can create different visual effects. Like here we have the gravity effect. Okay, so let me introduce the pipeline a little bit. So the basic problem is that we have a container. Here is the elephant, and we have a set of objects like the green circles here. Actually, it's not circle, like the green elements here. So we start from this set of 2D geometric items that normally is described in SVG, is in vector form. And so we use the differentiable rendering to render this set of objects into image. And we get something like this. And on the other hand, we have a container, and we also render this container into an image so that we have two images. Then we can design the image-based loss to quantify how packed currently the layout are and how many empty space there are. So with this image-based losses, we can easily backpropagate them into the object space. Here, we use the loss to optimize the rigid geometry transformers, such as like to translate, to scale, to rotate the 2D objects. Then the the process iterate until the laws converge to what we want. And a nice thing here is that because we work in like image space, so we can play with the different resolutions of the images. Like, say we can have a hierarchical rendering strategy. So in very beginning, we use very low resolution for fast converging, and in the end, we increase the resolution to do fine tuning. And here shows some processes that we have during the optimization. We can see that this method can deal with different elements, like the text here or like the star here. And the optimization process is smooth because we use the descent gradient optimization method. And so with this technique, we can assist designers to design some nice collage. And here I show a poster that I designed. So I take the container of these two animals and feed it up with the icons of the related to a topic of environment pollution. And here shows another design that I create, that I take the container like this. And we see here the container have holes and concave boundary here. And I feed it up with the text. Okay, so actually in this project, I didn't use any of generating models. We solved an optimization method. And now let's switch to another topic, which I will talk about stylized image generation. So the main idea of stylized image generation is to generate some nice images that are stylized and artistic. Actually, this direction has already been studied for decades. Researchers propose like painterly algorithms to paint an image. Like here is like sketchy style. Or in recent years, researchers also study to leverage the power of generating models to generate something like artists who draw it. Okay. So among these directions, style transfer is actually a very interesting and a popular research problem. So a basic style transfer problem goes like this. We have a content image, and we have an image that represents the style that we want. So style transfer is to transfer the style from the reference image into the content and generate something with the style aligned with the reference. And here is a representative of style transfer work. So we also work on this direction, but before I introduce what we did, let's first see Nano Banana. So Nano Banana actually is a very powerful image generation and editing model that we know that we can feed Nano Banana a reference image and ask Nano Banana to generate something that the text here conditioned. Say we want Nano Banana to generate an ice cream product poster from these three girls. So Nano Banana is very powerful and it can really generate something very nice. Like this is one of the results that it returns to me. We can see that the identity of the three girls actually are very well preserved, and everything is so perfect. Say they have 5 fingers and they hold ice cream. But this is an image generation example driven by text condition. But what if we try Nano Banana with a style transfer method? So I give Nano Banana this image as input, and I also give Nano Banana a reference image like this. Here I use an illustrative style. So I want Nano Banana to generate this image in this style. And this is what Nano Banana returns to me. Actually, it's not bad because we see that Nano Banana succeed to do some to learn something from the reference, say the color, maybe some texture, but we would say that it's not really style aligned with the reference. So if we tried it with some state-of-the-art style transfer method, this is one of the results generated by style ID, which is a SOTA method in style transfer. We can see that basically they transfer the colors, textures from the reference, but fails to learn some high-level abstractions. And this is the result that generates by our method. I would say that our method can learn the visual language that artists had in this reference and to re-express the input image. So now let me put them side by side. We can see that, for example, the feet of the three girls, we see for Nano Banana and some conventional style transfer method, the shape of their shoes are basically like to take the original shape of the shoes from input, but from the reference style, we can see that in this design, the shoes has already been abstracted into like a little dot. So in our results, it's really represent in that way. But to solve this problem, you may ask, what defines a style? So there is no clear definition of what is a style, but I think we can probably define a style by looking at a set of examples. And style may be something that is common shared among examples. Say we have a collection of these elements represent the same style, and we take one example out, we see that style is definitely related to the colors, textures that artists used in this style, but it's beyond that. It's also about how artists represent the head, the body, the shoes of the humor, like in this one. So when we consider this style transfer problem, like we have a realistic photo as the input, and we want to transfer illustrated style like this to this realistic person. What it's supposed to be. Like if we only do color texturing, we will get something like this. This is good, but it's not very close to the style here represent. So what is missed is here, like not only do color texture, we need to understand the geometry, the shapes beneath this reference, and to re-represent this object, these people, like something like this. Maybe this is closer to the reference in terms of style. So we think for this part is something that related to abstraction. And abstraction actually is a very common artistical practice that designers or artists they do when they develop some visual design style. So in this work, we emphasize on this abstraction and try to do style transfer with the consideration of how to learn this abstraction and transfer to new content. And here, I show a very extreme case that generated by our method. So we have this take as an input, then we have the reference, and we see here the house is really very abstract style. And we see this is the output. Here, not only color texture be transferred, but geometric wise that we we kind of do abstraction of the input image. And this is a work that we will present it like in next month in SIGGRAPH. So we want to learn abstraction and transfer to new content. But actually learning abstraction, at the very beginning of this project, I found it's very hard and challenging because we want to deal with different styles. And here we show for different styles here. We see that for each style, they have very different abstractions. Like in this one, designers use like boundary sketchy to simplify the object. And in this one is also very abstract, has its unique abstraction. So how can we come up with an algorithm that can generalize the learning and the transfer of the abstraction? So let me first show you some results. Here we have 3 different target image. And our method can take like 5 examples of a certain style. Then we can learn how to generalize this style to different targets like the 3 shows here. And we change it into another style, and it will be the result like this, and here is like this. So when we look at different styles, we can really see that of course color and textures are transferred here, but geometric from geometric perspective, also they change, like the wings of the birds here is like a round circle because here the style is more like regular shapes, and here is like very sketchy style. So let's look a pair of examples like the golden fish here. We see that the eyes of the fish is differently represented in different styles. Also, we see the fins of the fish. Here is very sharp triangles, but here is like a human sketchy style. So, so for this, we also compare to state-of-the-art method, and we see that most of the style transfer method, they transfer the colors, textures, like pixel level features, fails to do geometric abstractions. Nano Banana did a good job, but I would say that it's not very fit in this style. Okay, so how we do this? We have a 2-stage process for this abstraction in style. So as it sounds like abstraction in style, we disentangled like abstraction with the visual appearance. So the first stage is to do abstraction. So in abstraction, we only considered how the object will be represented in by shapes. So in this stage, we will generate a middle representation called the abstraction proxy, and basically it's an image. It's a gray image. So we see that in this stage, the geometry representation of the low bird is changed. We see the lines here is get thicker, and also the feet here is get different. It changed different, and then it go to the next stage. It's called stylization, and in this stage, we care about what color to use, what texture to be transferred, and then we finally get these results. So, so the key is how to do structural abstraction. The goal is that taking an input image and with different structure reference here, I show 3 different structure reference, and we want to reimagine this object according to the geometric features that represent in this reference. So by our method, the three abstraction process will goes like this, and we see they are very aligned to the reference that we have here. Like here is more triangle, and here is like more round and with figure lines. So how we do that? So consider this problem. We have the input image and we have a reference. We want to change the geometry of the input image into this abstraction proxy. And we didn't go directly from the input image to this abstraction proxy. We do an image process first. That is, we do image vectorization. So we vectorize this image and then we get simplified shapes from this image. But here we see that those shapes basically have the similar contours to the input image, and it's far from what we want here. So how can we transfer this simplified image according to the reference and get this? So when we think about it, it's like a geometry transformation problem. And it's a very challenging because we want the transformation method to be generalized to different reference here. So we shift this problem a little bit. We make it like an image space generation problem. So what we do is like, when we get this simplified image, we first do some geometric relaxation that we compute something underlying of this simplified image we call the hidden backbone. And the idea of this hidden backbone is to represent the structure of the input image without the precise boundary, so that the model can reimagine the geometry from this backbone without the constraints to the original input. Okay, so the way that we compute this hidden backbone is totally in image space, that we calculate the median axis of each shapes here. So for the long shapes, we have this thicker lines here. But for large shapes, like the balls of the plant here, we also add some the gray area that we do erosion, and we get this gray area, and to maintain that, to hint that this shape is large, we cannot take it as a line. So with this hidden backbone, then we try to learn how to generate this output according to the reference. So basically, this is a visual analogy task. So visual analogy task is actually it's a concept that has been already proposed by researchers before. So visual analogy task goes like this: we have a reference from a pair A to A prime. So this is from the reference example. And then we want to do the inferring that given the B, what is the B prime look like? So this is a visual analogy problem. But how to solve this visual analogy problem is try to learn the mapping from A to A prime. And if we do this in geometric space, I think it's very hard. So we ship this as an image in painting task. So we designed this 2x2 grid. So the inpainting is trying to inpaint the bottom right corner of this image according to the reference. So to train this image in painting, we leverage a powerful image in painting backbone model, FluxView. And basically, idea is to fine-tune this model with a LoRa so that the model can inpaint this area. So to fine-tune this LoRa is actually very simple, that we prepared like 10 images of this kind of 2x2 grid from reference, so that the LoRa can really learn what is the mapping from A to A prime, so that it can generate B prime from B. Okay, so here shows more examples for each law, we have the same backbone and we train different visual analogy LoRa, so it can generate different geometry from this backbone. And we see for each column, they share some similar geometry and like here. Okay, so the basic idea of the first stage is to do structure abstraction, and we use a visual analogy transfer and to get this abstraction proxy. So for the second stage, actually, it's the visual stylization, and we applying the same mechanism, but we change what we put in this 2x2 grid. So we put the proxy here and the final output here. So we trained a LoRa to learn what is from this proxy to the final output, and then it can impend this. We get this. Okay, so here I show different several results. For the input image, we have the backbone. We first extract the backbone. Then for different style, this backbone will be imagined into different styles. So this is what the underlying proxy looks like. We can see that geometric wise, they are very different from one to another. And from this to this is like the color textures. And so we look this into detail. So we have the abstraction visual analogy transfer to do structure learning. And then we have the stylization visual analogy transfer to color to texture. But people may ask, why not directly do analogy from the backbone to this final output? So we did a ablation study. A direct visual analogy would fail because we think there are too many things to learn from this mapping. So the model fails. And a nice thing for this distangling of abstraction and visual appearance that we can mix up the structure to and with the style. Say we have the structures here, and we can mix with different style transfer to get different styles, like we see here. Yes, it's like a stamp style. Okay. So here I have a little quiz, and we mix up the examples that we generate by our model with some examples designed by artists. So I think this is like a Turing test for style transfer. Can you tell which one is generated and which one is original from the designer? Actually, these three are from the original design, and other six are generated from the input image here. And here is another example, and those are the one generated by our method, and this one are the original one. Okay, so let me conclude it. So in this project, we do style transfer, but what we tackled here is that in conventional style transfer, they really consider abstraction. Like abstraction here is more specific to the geometry, the shapes. And so we introduced the notion of abstraction in style, and we want to learn this abstraction, and this is the result that we generate. So you can understand that our method is like shape level style learning and a transfer. And we present a two-stage method to realize this concept. So our method can take the same input image and then generate different results according to the reference. We see that how their shapes are different from one to another. And we see that we deal with really abstract style, and when we take some realistic image like this, the model can still generate some abstract, a very abstract from this realistic image. But I want to say that I think what we proposed in this SIGGRAPH paper is kind of an implementation to this concept, but the abstraction style is actually broader than what we achieve. So I'm really looking forward for further advance in this direction, and I'm happy if you have any questions. Okay, thank you. Thank you, Aichao.
Thank you. Thank you. Yeah, thanks, Min. Yeah, thank you for the nice presentation. So I will first forward like two questions in the channel, and I personally have some other questions.
Yes.
So for the first work, I think there's a
Mhm.
question about, is there any quantifiable boundary for the trade-off between data fidelity and visual aesthetics? So I guess it's more about whether
Mhm.
for the optimization result, like I think you have some loss function try to optimize for example, there's no overlapping and try to fit the
Right.
whole shape, right? And
Mm.
but sometimes how to, for example, is there any way to find to optimize for the aesthetics as well, or is there for the packing result? I'm trying
Okay.
to interpret the
Yeah, I
questions.
can
Yeah.
understand. Okay,
Yeah.
so in this work, we don't have quantitative metrics to measure the aesthetics. So we don't have that. Because aesthetics actually is very hard to measure, I think.
Yeah. Yeah.
And yeah, but we do have several quantitative metrics to measure the ratio of overlapping between
Mm,
elements
mm,
and how they
mm,
is exceeding the boundary.
mm.
And
I see.
I want to emphasize that different from Michel's work, like Michel works on very geometric solution that can ensure the hard constraint. Here
Mm,
we work in image space. It's more like a soft geometry
mm, mm, mm.
constraint. So we cannot guarantee there is no occlude, there is no overlap. Yeah. But we do have a set of quantitative metrics to prove that our method is kind of the best of the state of the
Mm,
art.
mm, mm.
Yeah.
I see. I see. I see.
Yes.
I also wonder from this work. So is there
Yeah.
any, so because I personally also working on some layout problem, and I personally interested is that is there any, for
Mhm.
example, maybe in packing itself there's a definitions there's no overlapping, but for this kind of similar design,
Mm.
is there any specific or similar design that they want to have, or they are okay with some overlapping? And if
Yeah.
there is it possible to extend this optimization framework to support that?
Yeah, I think I work in visualization. So in
Yeah.
visualization, there is a kind of visualization type called unit visualization. So unit visualization is like to use an element to represent a data entity. So in that
Mm,
kind of visualization, I think overlap
mm,
some design is what is desired. Like
mm, mm,
designers can allow, and also like sometimes designers want margin of
mm,
it. Oh,
mm,
like they sparse distribute. So it's very practical to to extend this method to cover both of two cases that
yes.
yeah, we do like consider this is like a fully packed layout,
Yes, 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 yes.
but we can actually render this icon smaller than what we had in the optimization. So we will have some space between these
I see, I see,
elements. Yeah.
I
So
see, I see.
yes,
Mm.
it's extendable.
I
Actually, we
see, I
have a
see.
work on that. Yeah.
Okay.
Yeah.
Yeah, it's not
Yes.
surprising. But 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 also so So there's a question for another work, but for this one and also for the next one, I think because
Mm-hmm.
this method and this algorithm are very, I think for me it's very useful. But I'm also curious about
Mm-hmm.
is there any, for example, collaboration with designer or like as you mentioned, you're working on visualization as well, and there must be some practitioner they really try to make all this like design or visualization, right? And
Right.
I'm just in general curious about what is their their feeling or their thought about like this algorithm. Do they want to try it a little bit, or they are kind of feels negative about all this automatic
Yeah.
kind of approach?
Yes, I think actually we open source our code
Yeah.
of this project, and
Yes.
there is really artists like to use that. But we have a now we develop authoring toolkits. Like we have
I see.
a
Okay.
yeah.
Mm.
So I in that project they feel excited because they are from experts from visualization field and they
Yes.
are more familiar with those interface uh,
Yes.
for
I see.
design. Yes.
I see. I see. Yeah, I think there must be some. So after after they use it, there must be some like a new problem probably will arise, and maybe it's also
Yes.
worth solving to
Yeah.
work with them. Yeah, I see.
Yes.
I see.
Yes. Yeah.
Yeah, and then for the second
Mhm.
project, so I think this question is kind of related to my personal question. So the question is about
Mhm.
like as the omni models. So I think it's this kind of large generative models or multifunction model become stronger with more data. And
Yes.
what enduring problems in stylization remains worth studying beyond scaling.
Mm.
Uh,
Yeah. So you mean that what is the scale that we use in training this data, this model?
no,
No?
no, I think the problem, my personal interpretation is that so for example,
Mm-hmm.
as you mentioned in the beginning, in the beginning of introducing this project, you mentioned
Yeah.
that for example, let's take a look at what Germany will do, right?
Yeah.
And I think coming with more and more like large, I would say closed source private models, and they are basically
Yeah.
training on like millions of data.
Yeah.
And I think this question is more about like, for example, if there's these kind of models,
Yeah.
and is there any other like open question or open like stylization problem to solve instead of
Okay.
just like let's just feed more and more data? Yeah.
Okay. Yeah. I think basically many image task has already been killed by those large models already. But I still believe there are space like in this abstraction style because we in this specific task we care about the reference style which is designed by designers so it's not they cannot produce many this kind of designs as training data. So it's like a small sample learning. I think for this kind of task, still there is space for researchers to work on. Yeah, and
Yeah.
consider the Olympic style that the Olympic
Mm.
has a very limited number of examples. So how can we transfer the style of the Olympic into like a regular person motion? I think it's hard for Gemini or like Nano Banana to do that yet.
Yeah. I see.
Yeah. Yes.
I also agree. This is like a very tricky situation. I think. Yeah. Well,
Yeah, but there
yeah.
is not too much space. We need to find
Yeah.
a very good problem.
I personally my personal question related to this is that like since nowadays if we are working on this kind of problems, and then during the review process, we are always sometimes asked by the reviewers saying, why didn't you compare with all these large models? And they are always generating some very, I don't know, appealing result.
Right. It's
And
tough.
yeah, what do you yeah, originally I want to ask you, what do you think about like this yeah, because I think that the model itself is, because we don't really know what kind of data they are training on, right? So it's
Right.
I personally believe the comparison is a little bit, I don't know,
Unfair.
unfair. Yeah,
Right,
and
right. I agree. I agree. But to make the paper accepted, I think the best way is try to include them as a baseline to compare. So really show that our results is like superior to others. So in
yeah,
that way, it will be very convincing. Yeah.
but
But
yeah,
it's tough.
it's very
Yeah.
difficult, I think.
Yes, it's tough. It's tough to work on that on this.
Yeah.
Yes.
Yeah. Yeah,
Okay.
okay, then I think that's mostly about it. And yeah, thank you for joining. Yeah, it's
Yes.
very nice to discuss on these matters, and yeah, hopefully, yeah, hopefully we can find a time to discuss in SIGGRAPH as well. Yeah. Okay.
Yes. Okay. Thank you,
Yeah.
Aichao.
Okay. Yeah.
Yes.
Thank you.
Okay.
Then yeah, I think that's it. And thank you. And I think we can just finish the talk, right?
Yes.
Yeah.
Okay.
Okay.
Yes.
Then yeah.
Bye.
Thank you. Thank you, Min. See you. Bye.
Yeah. Bye.
See you. Good night.